Hello viewers, welcome to Gurukul lectures. Myself Dr. Preeti Jagwani, I am from Department of Computer Science, Aryabhatta College, University of Delhi. Today's topic is potential method, which basically falls under the umbrella of amortized analysis. So till this point we have covered many lectures in amortized analysis or for amortized analysis topic, and we have seen what actually amortized analysis is, and then we have seen aggregate method and accounting method. So let us recall accounting method in a nutshell. We can say accounting method represents prepaid work as credit stored with specific objects in the data structure. Now the important term here is the credit stored and specific objects. I will be taking this why these two terms are very important, in fact, if we are talking about potential method. Now coming to potential method, we can say in some way is similar to accounting method, and it is also having its own distinguishabilities. So potential method is basically there to represent the prepaid work as potential energy, while the accounting method represented that prepaid work as the credit, or in potential method we will represent prepaid work as potential energy, or we can say just potential to be convenient, and this potential is stored in order to release or in order to pay for future operations. And this is what we have done in the accounting method also, but in a kind of we can say different manner. There the credit was stored and it is released for the future operations. Similarly here in potential method we will be storing the potential or potential energy, and it will be used to pay for further upcoming operations. So this potential method is also known as physicist method, because here we are dealing in terms of physics if we are talking about potential or potential energy. So this is basically known here as physicist method. In this, what are we going to do? We are actually going to make out or determine or derive a potential function. That potential function is going to give us the amount of extra work done in each step or for each operation, we can say. So after every operation the potential is either going to increase or going to decrease, but it cannot be negative. So please recall, in our accounting method we have said that credit cannot be negative. Similarly here the potential, either it is going to increase or decrease with successive operations, but it cannot be negative. We cannot have a negative potential, or we cannot have negative credits in the previous method, which was accounting method. So now this potential is determined on the basis of a potential function which is chosen in order to map the state of data structures to some positive numbers. Now let me repeat this step here. The potential function is chosen such that it is going to map the states of data structure to positive numbers or non-negative numbers. Now while in starting when I was recapping the accounting method, I insisted two terms. One is the specific objects, another one was credit. So credit here is a kind of we can say potential energy or potential here, while I have also insisted on the term of specific objects. In accounting method when we say that credit is stored with specific objects of the data structure. For example, I am talking about a stack. So in that stack the credit is going to be associated with individual elements of the stack, while here in potential method what are we going to do? The whole potential energy or potential is not associated with the individual specific objects of the data structure, but it is associated with the whole data structure in not with the specific objects, and this potential function is going to keep track of pre-charged time or pre-charge, we can say, complexity at any point of time in the computation. That means we are having some pre-charged or stored time to be given or to be allocated to some future or further operations. So this potential function is going to keep track of that pre-charged time at any point in the whole computation. Now let us explore more about this potential function and potential. So the potential function is there to measure how much saved up time is available to pay for the upcoming expensive operations, and this potential, as I told you, is associated with the whole data structure rather than with the specific objects within the data structure, as we did in accounting method. In accounting method, it was with the specific objects, the credit was with the specific objects. Here the potential is with the whole data structure, and this potential basically is, we can say it's a kind of scale, or it's a kind of measurement that how much amount or how much credit, or we can say how much potential energy, how much time we have in our storage in order to pay for the upcoming expensive operations. So basically this potential function is going to keep track of the pre-charged time at any point in the computation. It measures how much saved up time is available to be released for the upcoming expensive operations. So what saved up time we are having and how much of that time can be released for future operations. These things can be, we can say, determined using the potential function. Now potential function, when, or the potential energy, if we talk about, so potential energy here is analogous to the bank balance in the banker's method or our accounting method, but it depends only on the current state of the data structure irrespective of the history of the computation that got the data structure into that particular state. So basically the bottom line here says we are going to associate the potential with the current state of the data structure, not with the history of the data structure, not with the specific objects in the data structure, but what we are concerned is actually the current state of the data structure. Now let us try to explore this point in somewhat detail. For example, we have let us say a data structure S, and we have some work which is, we can say, is already paid for, that has been accounted for or paid for in the amortized analysis, but not yet performed. That means we have something in our storage, and phi of S is going to represent the work that has been accounted for or that has been already paid for in advance for the operations which have not been performed. Yes, so phi of S here is going to be kind of amount of potential energy stored, or is this going to be the thought of as calculating the amount of potential energy stored. So S is a data structure, phi of S is actually we can see it as calculating the amount of potential energy stored. So phi here, we can say the term phi is the potential function, and we can say alternatively we can also say that phi of S may be thought of as representing the amount of disorder in the state S or its distance from an ideal state. So we can say that S is, let's say, a state of a particular data structure, and phi of S is representing how much that state is being deviated from the ideal state. So if we talk about the potential value or the potential amount of potential energy which is available prior to the operation of initializing a data structure, that is to be defined as 0. So that means if we are talking about the initial state of the data structure, the potential value at that time, at that point of time in the initial state of the data structure will be defined as 0. So potential value prior to the operation of initializing a data structure, that is the initial state, is defined to be 0, and this is very important concept here. Now let us say as we have seen that potential function is generally denoted by the symbol phi. So a potential function phi which is defined for the states of a data structure can have or must have the following properties. Phi of h of 0 is equals to 0. Now let us try to understand this, what actually it is. Phi here is the potential function, h0 represents the initial state of the data structure, and as I have just said that phi of h0 is equals to 0, that means in the initial state of data structure the potential energy we have as 0. So phi potential function when applied on the initial state of the data structure, which gives us as phi of h0, that is equals to 0. That is one point here. Then we have another term which is, we can say, phi of ht. Phi of ht is going to be greater than equals to 0 for all the states ht of the data structure occurring during the course of computations. This essentially means that in whatever state your data structure is during the computation or while performing many of the operations, this phi of ht is always greater than equals to 0. So here comes the concept when we say that, here comes the concept of saying that credit cannot be negative or our potential energy cannot be negative. So here is that particular point which we are trying to express mathematically with reference to potential function. So here we say phi of ht is greater than equals to 0, and this ht can represent any of the state, or we can say this ht is going to represent all of the states of the data structure which are occurred during the course of computation. So it could be h1, h2, and whatever the states are. For all the states, phi of ht, which is the potential function when applied for a particular state of the data structure, is greater than equals to 0, while for the initial state of the data structure this is going to be 0 only. So t here could be 1, 2, or whatever, any state of the data structure here we are talking about. So phi of ht is greater than equals to 0 always. Now coming to what is the amortized time for an operation. So amortized, while calculating the amortized time of an operation, we have seen that earlier we have considered that here what we are focusing upon the state of data structure. So the state of data structure before that particular operation and the state of data structure after performing that particular operation, and within a state also what are we looking for specifically? We are actually looking for the potential energy or the potential of the data structure at a particular state. That means the potential of the data structure before performing the operation, whatever the state of data structure is, and the potential of the data structure or the potential of the state of the data structure after performing that particular operation. So while calculating or while determining the amortized cost of an operation, we will be taking these two terms in consideration. So the amortized cost of an operation is going to be C plus phi of h dash minus phi of h. Now let us try to understand what these three terms are. C is actually C is the actual cost of the operation, we can say, and we are actually calculating amortized cost. So C, the actual cost of the operation, while h and h dash are the states of data structure before and after performing that particular operation respectively. That means the h dash is the state in which my data structure is, we can say, lying after performing the operation, and h is the data structure, h is the state of the data structure in which the data structure was there before performing that particular operation. And when we talk about phi of h dash and phi of h, that means we are talking about the potential for those particular states. That means potential for the state h dash and potential for the state h. So when we are saying C plus phi of h dash minus phi h, that means here phi of h dash minus phi of h is representing the change in potential for that particular operation, because phi of h dash is the potential before performing the operation, and phi of h is the potential of the data structure after performing the operation. So phi of h dash minus phi of h is, we can say, actually representing the change in potential of that particular data structure, and when it is added with the actual cost C, we are going to have the amortized cost. So in short, we can say the amortized cost of an operation is actual cost plus change in the potential of the data structure. That is what the formula is, and the potential, change in potential of the data structure is represented by phi of h dash minus phi of h, where h dash and h are the states of the data structure after and before performing the operation respectively. Now, so we can say, as I have told you, the amortized time is the actual time plus change in potential. Now, when we talk about the term potential function, which is phi, so phi should be defined so that amortized cost of amortized time of each operation is small. So in accounting method, we, if you can recall, we have seen that how we are going to take our credit function. So similarly here we need to focus upon potential function, which is phi. So it should be defined in such a manner that amortized cost of each operation is small. Now if I am talking about change in potential, so if it is a low cost operation, the change in potential is going to be positive, because we are subtracting the phi of h dash minus phi h, and if it is a high cost operation, it is going to be negative. So we can say change in potential should be positive for low cost operation and it should be negative for high cost operations. Now here we have seen just one transformation of data structure from one particular state to another state, which was h and h dash. Now if we are talking about, so if we can recall the concept of amortized analysis, we always talked about a sequence of operations. We never considered one operation individually in when we are talking about amortized analysis. So here if we are saying that my amortized cost is equals to actual cost plus change in potential. So this change in potential should be taken into account for a sequence of operations, and within this sequence of operations, the state of data structure will change with each and every operation. So now let us try to focus on the what will be the amortized time or amortized cost if we are talking about a sequence of n operations. Now consider this sequence of various operations, and this sequence of various operation is actually taking some times like C0, C1, C2 till Cn minus 1, and what data structure it is producing is here we can term those data structure in terms of states starting from H0 to Hn. So for state 0 the actual time taken is C0, and the earlier state was H0, and now the data structure is going to be converted into H1. Considering similarly this for state 1, the data structure is in state 1, now it will go to state 2. So that means the transition will be from H1 to H2, while the actual time taken for this is C1. So here we need to sum up all such states. That means we start the data structure initially, which is we can say initial state, and that from that initial state if we are going to perform n operations, the last will be h of n. So we have started from H0 and we will be going till h of n, and for all these states from 0 to n we need to sum up the total amortized cost. That means the total amortized time is going to be the sum of individual amortized time. That means we will be taking individual amortized time for each and every states, and we will be summing it up. It's a simple concept that total amortized time will be equals to sum of the individual amortized time. So we have seen how to make or how to take one amortized time for one state. Now let us try to consider it for n stages. So for n stages, that particular expression which says the amortized time is equals to the actual cost plus the change in potential will happen for all these stages. Now let us see how. So this is going to be C0, which is the initial cost for the let us consider state 0. So here the earlier states was 0 and the new stage will be 1. So the change in potential will be represented as phi of H1 minus phi of H0, that is the new potential minus the old potential, plus C0, which is the initial cost, is going to give me amortized time for the stage 0. Now coming to stage 1. Stage 1 says this will be C1 plus phi of H2 minus phi of H1. Then we need to do this for all the terms. So the last says Cn minus 1, which is the initial which is the actual cost for nth state Cn minus 1, and change in potential. Change in potential says phi of Hn minus phi of Hn minus 1, which is the potential of the previous state. So here if we use the telescopic term, we have telescopic series, we will be having C0 plus C1 plus C2 plus till Cn minus 1, and the terms which will be left in the corresponding the potential, that will be phi of Hn minus phi of H0. Other terms will be we can say cancelled here. So phi of Hn minus phi of H0, and please recall we have seen that phi of H0 is equals to 0. So phi of H0 is 0. So we can say the expression becomes C0 plus C1 plus C2 till Cn minus 1 plus phi of Hn. This is going to be the sum of amortized times for the n states. So yes, we can say amortized times for a sequence of operation overestimates the actual time by phi of hn, and which is by our assumption it is going to be a positive number. So we are adding a positive number into the actual cost for determining the amortized time. So we can simply say that total amortized time is an upper bound on the actual time, and this is what we have discovered in other two methods also of aggregate analysis and accounting analysis, that amortized cost is always an upper bound on the actual cost. And here also we have established this fact that we are adding one term which is phi of hn, which represents the potential at the nth state, and by our assumptions this is going to be positive. Because of addition of this positive number, amortized time for a sequence of operation is overestimating the actual time. So this is what we established, that total amortized time even in physicist method or even in potential method is an upper bound on the actual time. So in this lecture what we have seen is what actually potential function is, potential method of the amortized analysis is, how it works, and how are we going to determine this potential function, or how do we a simple math with this potential function. Hope you have enjoyed the lecture. Thank you.